Dear Spark fans, welcome to another session, Data with Nikk the Greek. You want to learn about Spark's main architecture concepts and also become an expert into it, then this session is definitely for you today. It's the second part of Spark Basics Simply Explained, so if you missed previous session, you should find now a link in the video, or you can also find it in the description below. We're gonna talk about the following topics today. So how the architecture is working based on two examples. So we learned previously how the architecture looks like for Spark, but now we're gonna look into a filtering and count example to see how Spark really behaves when it processes data with those two operations. Then we're going to talk about lazy evaluation, catalyst optimizer, one of the main reasons why Spark is so efficient due to its optimizations in the background. And then we're also going to have a look into what's the difference between actions and transformations, which is really important to understand, as actions are actually the driver of performing an execution within Spark. And last but not least, we're going to take a look into jobs, stages, and tasks, which is basically how Spark is structuring the execution plan. So there is some kind of hierarchy within, and this you're going to learn within this video in a bit. Before we're going to start, as always, just to mention, if you like this video and you also want to see more videos like that, feel free to subscribe to the channel. You're going to see on the right side below this video a red button. So just click on it and you're subscribed already to see more videos of it. If you have some quality issues, I also want to mention there's also settings button below this video. You can just increase the quality of this video and then you can properly enjoy it. All right, let's start with the first part of the architecture deep dive within Spark, where we're gonna use a very simple example, filter and write. Filter is our transformation, write is our action, which lets in Spark execute the calculations. And it looks pretty much like that. So we create a data frame. Here we have just a very simple data frame, 12 rows, but imagine it's a very big data set. And then we want to filter it with all rows available which have column 1 value below 10. So meaning in this case, we filter out the last 3 rows of this data set. And then we want to write the data set. And if you remember, we have this following architecture as an example. So we have the driver who is telling the workers, or sometimes also called executors, what has to be done. And then we have the cores. So each worker in this case has 2 cores, which are basically the actual areas where work can be done. So that's where the partitions, the pieces of data, which we see now on the top left side, actually basically executed. So what Spark is doing is we have the full data set and it cuts it into small pieces, and those pieces are basically called partitions. So, and now what happens? So the driver is saying, because he basically manages what the workers or executors are doing, it says, okay, core 1, please execute partition 1, core 2, execute partition 2, and so on. And that's where the parallelization is happening. So that's also what is called a task within Spark. And now it says, okay, you have the following instruction, please filter everything below 10. So what happens is worker 1 to core 1 and 2 in worker 1 and the core 1 and worker 2 don't need to filter out anything because this value is not there, but the second core in worker 2 has no data, and then each of those cores are basically saving the data in parallel. So it means also when you're looking later on in Spark and see how the data has been written in this case, you're gonna find 3 files. Why 3 and not 4? Because the last partition is basically empty, so there will not be any data. And that's basically the whole thing about partitions when you do a filter and write. So what's the takeaway here? So we saw that Spark is distributing the data processing based on the partitioning. So the driver coordinates, the executors or workers are doing the doing, and the course of each work has processed one partition, and this is called a task. And also what's important to mention here, so each of those executors are sharing the same disk memory and network. So now let's take a look into another example. So we just do a simple count. So there's no filtering, we just directly go with an action. So again, we have the following data set, so 12 rows. And well, I already told you the result. The count of those number of rows should be 12. And again, we have the following architecture. So we have a driver, and we have two workers or executors with each one 2 cores. And again, we have the same data set split it in the same number of partitions. So again, the driver says, so core 1 execute partition 1, core 2 execute partition 2. Just in this case, we're not doing a filtering, we're gonna do a count. So each of those cores is counting the number of rows completely individual. So that means core 1 in worker 1 results in a 3, core 2 in worker 1 results in a 3 in our example, and so on. So, and now what's happening is the driver says, okay, count the rows, but also persist the results to disk, because we have to persist them somehow. We could also return them to the driver, but per definition, the driver is not allowed to touch the data. And then what happens in the next step is, okay, one core gets a task. Please collect all the subsidiary results of each core and perform a count on a count. So basically, there's some second iteration which we have here, basically. So, and then finally, the core 1 who executed the second round of counts can return the result to the driver, and that's the only time the driver is actually allowed to touch the data, in this example at least. And that's how Spark is calculating that we have 12 rows. And now imagine that, of course, with million or petabytes of data. So that means what we learned here is that Spark, in the example of counting, creates 2 rounds of execution. So first of all, we have a local count where we count the data of each partition, of each task, and save the data on disk. And then we have a second stage performing the final count. And also that the driver is never allowed to touch the data except when taking the result. Now let's talk about lazy evaluation, the catalyst optimizer. So last time we had this example. So on the left side we see a Python code, reading a Parquet file, filtering, and performing the count. And on the right side we see the example written in Spark. So, and the difference is when you execute in Python, it performs each line of code directly and executes it. What lazy evaluation on Spark side actually means is that it performs an execution, an operation first when there's an action, for instance, a count. So meaning when you're gonna execute the read and the filter, nothing really happens, but only once the line with the count is executed, Spark starts working actually. So, and this is called lazy evaluation. And the benefit of it is that you can collect all the operations, and Spark has a chance to optimize them using the catalyst optimizer. And this leads to a more efficient execution plan. And before we're gonna talk about the catalyst optimizer actually, we should just talk about a concept which is called DAG, directed acyclic graph. So basically it's created as actions are doing the execution. Also the DAG is created when an action occurs, and it represents all the operations to be performed in an acyclic way. So it's a sequential step basically. And Every edge represents an operation on RDD level, so resilient distributed data set. So that's a core data set structure of Spark. And well, it represents a data frame in a Spark core, basically. And also the graph is divided into something called stages. We're gonna see it in a little bit, what it means in detail. And also by that you have some fault tolerance, because for each partition we know where the data is coming from. And then if one of our executors or cores doesn't or isn't able to execute a partition, we can basically cancel it or let another core in parallel execute the same partition. And that's like also really important in Spark, what's possible. So, and as an example, so that's not the real acyclic graph, but just as a conceptual example, we, for instance, might have, as seen before in the Python code, we load all the data, we filter by ID, we make a local count, we make a global count, because we already learned that we have basically two counts which we're performing when we do a count operation. And then the DAG is used actually by the catalyst optimizer. It says what has to be done, and then the Spark optimizer, catalyst optimizer basically creates the instructions to do those operations in the most efficient way. So, but what is the catalyst optimizer basically? So here I have a nice graph. I don't want to go into the very detail, but I want to cut it down a little bit what Spark is doing in the background. So basically it's a rule-based engine which I think has been introduced like around 9 years ago within Spark, with Spark SQL. And it provides a logical plan, which we saw before, roughly said, in the DAG to an optimal physical plan. And how it's doing it, it's basically doing it in multiple steps. So first of all, we have a so-called unresolved logical plan where we haven't seen the metadata, etc. So basically in the analysis phase, we are checking our catalog, for instance, and basically all the metadata which is available for the columns and tables. So do the columns, for instance, exist? And also the metadata is important for further optimizations. So that means we, at the end, have a legit logical plan. So with approved legit tables and columns, and also some commands might be reordered to be a little bit more efficient. And then Spark is creating an optimized logical plan. So this is happening rule-based. So your code is basically rewritten, you could say. So one example is a predicate pushdown, for instance. So filters are pushed down and filters are combined together because Spark thinks it's more efficient for you. And then it creates multiple physical plans that can be used to execute the query. And then we have a cost model where the, well, most cost less expensive physical plan is used. And then Java code is basically created, and the RDDs, so the core structure of Spark, is then executed in the background. And I just want to take our example which we had before. So before we had something like we load all data from a Parquet file, let's now assume, or actually we had it for a Parquet file. Then we filter the ID with above 10,000, but that's exactly the trick where Spark already says, does it make sense to load all the data if I just need to filter based on the column ID? And I just want to make a count. So what's the value of having all the data available in Spark? So Spark uses the predicate pushdown, which is possible with Parquet files, and says, okay, I'm only loading all the rows of the available data set in the Parquet, but only with the column ID. And if you have like 20 columns, it might reduce the data which we are loading into memory already by a factor of 20. And this speeds, of course, the process up, but also like reduces the number of executions you have to do. And also you need less resource because you need in total less memory to resolve this execution. And then we do the local count and global count. If you would even leave the filter out in predicate pushdown, because Parquet is saving the metadata also for max and min values, and so on. It might even speed up the count. Well, it saves the metadata also of the number of rows. That's why it gonna speed the count. Sorry for the misspoken. But important is it optimizes it in a good way so that you're gonna be more efficient at the end. So that means takeaway. So we have lazy evaluation, which means Spark will only start processing with an action. We have the DLG, directly acyclic graph, which represents the planned operations and also has fault tolerance, and it's the input of the catalyst optimizer, and then the catalyst optimizer is basically optimizing your written code. So now let's go into actions and transformations. I think by now we learned it and saw it already, but just to summarize the topic one more time. So actions are basically the methods which perform an execution in Spark. So this really makes the data available in a data frame as a result, and it executes all the related transformations as defined. So we saw it before in lazy evaluation. So Spark executes only if you have an action. And examples for that is a count, what we saw before, a show, a collect, first, take. Okay, I forgot the right, also important here. And then we have transformations, which basically in the background are resulting in a single or multiple RDDs in the background of the core architecture. So we have narrow transformations, which we mainly talked until now. So narrow transformation means they can be executed in parallel. So an example is a filter, a select, for instance. And then we have wide transformations, which similar to the count, it requires some data movement. So imagine aggregate, for instance. So if we want to, or a group by. So if you want to group by a specific column, but you might have the same value in multiple partitions, then you have to shuffle them a little bit around so that all the cores have seen like the same data. So that's a more complicated concept. That's something we're gonna do in another session. But basically important that there are transformations which need to look into multiple partitions and shuffle and move the data around between partitions to perform this operation. So in this case, usually what happens is we probably would sort the data before we're gonna do the group by based on column 1, for instance, and then perform the group by, because then you can be sure that in each partition you're gonna have the same column. So last but not least, jobs, stages, and tasks. So first of all, what's important is we have a hierarchy. So we have one or multiple jobs, and then each job has one or multiple stages, and then each stage usually has at least as many tasks as the number of cores we have, because otherwise we would not use all the cores. And that's something really important. If you don't use all the cores, you might have done something wrong within your code. And what's also important is jobs and stages usually run sequentially. So for instance, within a join, the stage might run in parallel, because you have two individual input stages there. And a job might also run in parallel if, for instance, you're gonna perform a threading or something like that. But the reparallelization Spark happens on the task level based on the partitions, as we learned before. So that's where the parallelization is happening. And what's the job? The job is the highest level of the execution. It's triggered whenever we're gonna have an action, and we have stages and tasks. um, underneath of it, as explained before. And a stage, so basically a stage divides the job into one or multiple of them, and this usually depends on the operation. So if the operation can only be done in serial, then we're gonna have another stage. And an example is basically the count which we had before. So to perform the global count, we saw that we need the local count. So basically that's an example where we had two stages in Spark at the end. So in the first stage, every core is calculating its local count per partition. And then we're gonna have a second stage, because before having the local counts, we cannot do the global counts, for Spark to calculate, to do the second stage with the individual counts per partition. And usually Y transformation also results, well, not usually, but actually nearly always result into multiple stages. So and then tasks at the end are the lowest level of work. Each task is federated across a core within a worker. So each core executes one task at the same time. And each task executes only one partition. So there's a very strong relation between partitions and number of tasks. And that's where the parallelization is happening. And as an example of one cluster, so a cluster is a combination of drivers and workers, has 6 cores, 6 tasks can be executed simultaneously in parallel. And with that, let's summarize what we learned today. So the first point is Spark distributed data partitions across multiple cores within the workers using tasks. Jobs have multiple stages, and stages have multiple tasks, and of course they're executed once we had an action. So we learned about transformations, actions. Actions is when actually the action is happening, so when something is executed. And then we have the concept of Spark is lazy. So we have lazy evaluation, and it executes after an action and creates DAG, direct acyclic graph. And this is then used to optimize your whole execution plan with a catalyst optimizer. And this increases the efficiency of an ETL workflow. And with this was everything for today. Thanks a lot for listening. If you like the video, like it below, comment below if you have comments or questions to it. And of course, if you want to see more videos like that, feel free to click below the red button and subscribe my channel.